Hello and welcome to FTC Team 13507's Control Award video submission.
Our robot uses a unique dual-camera setup, simultaneously running two vision pipelines. The first camera, facing the front of the robot, is used for detecting disks during the teleoperated period. It uses a Kotlin-based contour detection pipeline. Essentially, when a disk comes into the field of view, the pipeline filters out any color except orange, and then decides if the remaining pixels have contours of the right shape. A circular object, such as a disk, will have the correct contour or shape, while a stray region of orange would likely not. This means we can cleanly turn on and off the intake systems without operator intervention.
The second camera facing the rear of the robot is used for detecting the high goal during teleoperated and autonomous periods. It uses an FTC lib-based pipeline known as a threshold. It detects all red or blue colors in the frame, then decides which area contains the most pixels of the correct color, which is the high goal. Finally, it draws a bounding box around the goal and returns information about the image. This includes the position of the image relative to the camera as well as the height of the image. We have tried several other vision pipelines for both cameras, including TensorFlow, Basework OpenCV, Vuforia, and Rex. However, we found contours and thresholds to be the most efficient and reliable pipelines for our application.
Roadrunner is one of the best solutions for field localization. Roadrunner keeps track of the robot's location at all times, using only the robot's odometry encoders, and generates the most efficient path to a selected location. In autonomous mode, Roadrunner is used to generate efficient paths around the playing field, which the robot follows at speeds near the max velocity of the drivetrain. Additionally, it allows the robot to precisely follow the same path every time. In the teleoperated period, Roadrunner is used as an operator augmentation. At the push of a single button, the robot will generate a path to our optimal shooting location on the fly and follow it automatically. Using Roadrunner, the robot's speed is significantly faster than if controlled by a cumbersome human operator. PID, or Proportional Integral Derivative Controllers, help Roadrunner to rapidly and finely control the position of the drive base. PID is a method used for error mitigation and correction on the fly. The proportional part of PID is the most obvious. The power of the motor is set relative to the error in the motor's position. The error is where we are minus where we want to be. Having proportional control alone may cause issues. The robot might oscillate around the target position, or might not respond fast enough to changing loads. This is where integral comes in. An integral term increases correction relative to how long the error has persisted. For example, if we are too far off to the left, and the proportional term's applied force is not enough to bring us to our desired position, the integral correcting force will be made stronger with time. A PID loop with purely integral values could bring the error to near zero, but the action would be slow to react. A system with exclusively P and I values, on the other hand, would most likely overreact to an error, overshooting and oscillating. That's where derivative comes in. Quite simply, it decreases the speed of the system as it reaches the correct position, thus eliminating overshoot. This system of error mitigation is used in our robot by Roadrunner, allowing the robot to travel at top speed while maintaining endpoint accuracy. Additionally, if the robot encountered an object in its path, such as a stray wobble goal, which catches the corner of the robot mid-maneuver, it will be able to correct its course. A PID controller is also used by our flywheel shooter for velocity control. It corrects the rotational spin down that occurs after each disc is fired, and allows each disc to be fired out at a constant rotational velocity.
This concludes our Control Award video submission. Thank you for watching.